So continuing on our vector spaces, we are going to talk about today a basis set. Now a basis set is a subset of a vector space V if the following conditions hold: that B will span the whole vector space, that is, every vector in the vector space V can be written as a linear combination of the elements of the set B, and the set B is linearly independent. So what we're doing is we are combining two important things. We're saying not only the set B is linearly independent, but also it is spanning the whole vector space V. This is the core of the base vector spaces, guys. Basis set is the core. Because remember, what is a vector space? Vector space has infinite elements. Now, if you want to prove something is a vector space, it's going to be very tedious. But if I can represent the infinite set by a few elements, and thus basically I'm working on the whole vector space. So basis set is that set which will represent the whole vector space by just few elements. And one more important thing, that you can have more than one basis set. In other words, the basis set of a vector space V is not unique. This is a very important fact, because if I can have more than one basis set, that means it's not a unique thing for a vector space. Okay, now this is something which is related to the basis set, and it is from section 4.5. This is called the dimension of a vector space. A dimension of a vector space, guys, is equal to the number of elements of any basis of a vector space V. So that means no matter how many basis set we have, there's going to be one important commonality between each of these basis sets of a vector space, and that is every basis set of a given vector space will have the same number of elements. And that this dimension of a vector space is denoted by dimension dim V. Okay, so remember what we just talked. We said a basis set. A basis set is a set of it's a subset, first of all. It's a subset of a vector space which is linearly independent, and it spans the whole vector space. Not only that, we can have more than one basis set of a vector space. So from there we're saying, so there's something called dimensions. Now the dimension is related to the how many elements are present in the basis set. That means the number of elements. So the dimension is equal to the number of elements of a vector space. Now remember, there are vector spaces which can have basis set to be infinite elements too. In that sense, so if I have a basis of a vector space which has infinite many elements, dimension of that vector space is infinite. Remember, there's something I want you to be aware of and not make a confusion. It's an idea if I can represent a vector space by a few elements, but there's a possibility that I will be representing a vector space by a basis set which has infinite elements also. Okay, so both of things are going hand in hand. Okay, so if you have a basis of a vector space with infinite elements, that means the dimension is infinite. Now let's look at some examples. We're going to go back to our M22. So here we're going to say, let's look at this basis set 1, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 0, 1. And I want to prove that this B, the capital B or whatever you want to say it, is a basis for the vector space of all real 2x2 matrices. So if I have to prove that this is a basis, that means first of all, the set has to be linearly independent. That basically means what? C1 times, this is A1, A2, A3, A4. That means C1 times A1 plus C2 times A2 plus C3 times A3 plus C4 times A4 equals 0. So we're basically saying if this vector equation is there, the only way this will hold is each of the CIs are 0. So it's a simple matrix addition and scalar multiplication and equality of matrices. So when we see this one, we say, oh, each of the CIs are 0. Clearly, this base B set is linearly independent. Okay. The next one, the B have to span the whole set M22. In other words, if I take any general element of M22, if any general element of M22 can be written as a linear combination of the elements of the set B. So clearly, if you look at this one, it can be written as A times 1, 0, 0, B times 0, 1, 0, 0, plus C times 0, 0, 1, 0, or D times 0, 0, 0, 1. So clearly, if I take any general element, every element can be written as a linear combination of the, a basis set. And hence, B is satisfying both the two conditions, and it is a basis set. Now remember, we talked about dimensions. Dimension of a 2 by 2 matrix of a vector space M22 is 4, because how many elements are there in this basis set? 1, 2, 3, and 4. So the number of the basis element is 4, and hence the dimension of this vector space is 4. Now this was an easy one. Let's pick up an element. As I said, remember, you can have many bases set of the same vector space. So I'm going to pick up another set, B, where elements are different, but it also is a basis set. Wow, let's look at that. So we have a set B, again, another set of the same vector space M22 of real numbers, and we're going to say that this also is a basis set, which proves what we just said in the beginning 5 minutes ago, that you can have more than one basis set of a given vector space. Okay, so as we said, this is the definition of a basis set. If it is a basis set for a vector space, it has to be linearly independent and it has to span the V. That means every element can be written as a linear combination of the matrices here, A1, A2, A3, A4. Okay, so first we prove that it is linearly independent. So we consider this L1, A1 plus L2, A2, blah, blah, blah. And we have to prove that each of the alpha i's are 0. The only way this equation will hold if the alpha i's are 0. And it's kind of guys cutting off, so this is simply alpha 1, A1. And this is basically consider. And keep in mind that I have posted all these notes on D12. So when you're looking through the videos, make sure that you have the notes also handy with you. So now what we're just simply going to go is we're going to plug these values. So this is the matrix alpha A1 times alpha 1 plus alpha 2 times matrix A2 plus alpha 3 times A3 plus alpha 4 times A4. Now remember, this is a 0 vector. Now when you're looking at this vector, we have to make sure that where are we coming from? What vector space are we coming from? Now this is an element of M22. That means every element inside this matrix is a 0 vector. And after that, it's a simple, very simple calculations. So we plug this one in, do the matrix addition, do the scalar multiplication, and we get this 2 matrices. Now, by equality of matrices, we can find the values for alpha 1, alpha 2, alpha 3. So this nice little computation is over here, and you know how to solve it. I'm going to show you another way of looking at the same problem. So either we actually have to do all these 4 equations and solve it, or we can use the idea we have learned so many times, that's section 1.1 and 2, guys, is that this matrix equation, guys, this little system, can be written as a homogeneous equation, Ax equals 0, where now the variable x is represented by the elements inside is alpha 1, alpha 2, alpha 3, and alpha 4. So what if I can say that each of this column is a pivot column, going back to section 1.5 and 1.7. All right, now this is 1.5. If I want to prove that this is linearly independent, I just have to prove that each column is a pivot column. Now, in order to prove that each column is a pivot column, what are we going to do? We're going to just apply the row echelon form to this matrix, the algorithm, guys. So when I do the algorithm on it, so what do I see? That every column of this row equivalent matrix is a pivot column. And hence, if every column is a pivot column, what we have learned is that the columns of this matrices are linearly independent. If they're linearly independent, that means alpha i's are equal to 0, which in turn basically talks about that the corresponding matrix equation here has only got the trivial solution. You know, notice how I keep on going back to the basics. Every time I've been saying, Chapter 1 is the key, guys. Chapter 1 is a key for everything we do here. Okay, now we have to prove that B spans M2 too. Okay, what does simply it means? Then I pick up any element of M2 too. So let's say it's A, B, C, D. I want to say that every element of of M22 can be written as a linear combination of alpha 1, A1 plus alpha 2, A2 plus alpha 3, A3 plus alpha 4, A4. Remember, these alpha i's, guys, are scalars or constants or coefficients or weights, whatever you are comfortable with. So then just plug in the matrices A1, A2, A3, A4, and then we get this, the equation, two matrices on the either side of the equal sign. Now we have to just basically solve the alpha i's, alpha 1, alpha 2, alpha 3, alpha 4 in terms of A, B, C, D. That's what we have to do. Okay, so when we solve this one, what do we get? So when we solve this one, we say alpha 1 can be written as B minus A over 2, alpha 2 is A plus B over 2. So clearly, each of these alpha i's, when you plug in this, will basically give us this matrix, any matrix of the vector space M22. So we have proof that B is not this matrix of B, which has different elements A1, A2, A3, A4, which spans the vector space M22, as well as it is linearly independent. So hence this B is the basis set for M22. And also notice, what is the dimension of this basis B? It's 4. It has 4 elements. So we are basically proving what we just said in the beginning of this video session, was that if you have a vector space, it can have more than one basis set. That's what we have. And no matter how many basis sets you will have for a vector space, there's a common feature among them that every basis set will have the same number of elements. That's proved. Okay, let's go and do some more examples. Okay, now we're going to see is that why this basis set, so this is something more deeper going into the basis set, that this basis set is an efficient spanning set which contains no extra vectors. Okay, remember what's a basis set once again. A basis set is a set which spans the whole vector space and it is linearly independent. Now, the same words are going to be tweaked around and said in a different form, that this is an efficient spanning set which does not have any unnecessary vectors. Okay, let's take a very simple example. So I have vectors v1, 0, 2, minus 1, v2, v3, oh, okay, whatever it is, v2, 2, 2, 0, v3, 6, 16, and 5. So notice this vector v3 is a linear combination of v1 and v2, okay? Now, if I collect all these vectors v1, v2, v3, we automatically know that if these vectors, when I take the spanning set, it is a subspace of R3. Okay, so this set H is spanning the whole of R3. But for it to become a basis set, it has to be linearly independent. Notice, if I can write one vector as a linear combination of it, it is not linearly independent. So that means this H is spanning, but it is not linearly independent. So can we actually get a basis set out of it. And how do we get that out? And that's what we're going to see here. Is that if I have a spanning set of v1, v2, v3, and this vector, which is an extra vector, if I remove this vector, will still it span? Let's see that. So this is a very important part. That when you remove the vector, which is kind of unnecessary, the span still remains, but it makes the set more efficient and hence becomes a basis set. Okay, so in order to prove that the spanning of these three vectors is the same as the spanning of these two vectors, what you're basically going to prove is something called from the set theory. This is a set. Remember, this is a set and this is a set. So if this is a set, say A, this is a set B. What it simply means is the set A and B are the same. At this point, they look different. Okay, to prove that some two sets are the same, we're simply going to say A is a subset of B and B is a subset of A. Guys, this is a symbol for subset. Okay, so first, if I have A is a subset of B, that means if I pick up any element in A, it will be an element of B. Go ahead, let's write that. So alpha is an element of v1, v2, v3. That means I can write it as a spanning set or a linear combination of these three vectors. And then we can combine them together as C1 plus V1 plus C2 and V2, C3, 5, V1, V3. We're replacing V3 by this relationship we are given. So then this whole alpha is basically now written in terms of two vectors, V1 and V2. Just give a new constant to it, K1, K2. So if alpha is an element of V1, V2, V3, okay, so if alpha is an element of V1, V2, V3, it is also an element of V1, V2. So that means we have proved that the set A is a subset of B. Now I'm going to take an element from B and prove that this is a subset of A. So let B be an element of spanning set V1 and V2, which can be written as M1 V1 plus M2 V2, and I can also write this as 0 times V3. So if it's an element of B, it is also an element of A. So we have proved that B is a subset of A. So clearly from both of them we see that the spanning sets are the same. The beauty of all of this is this, that if I have two sets who are spanning sets and I keep on removing the unnecessary vectors, the spanning set is not affected. The only thing which happens is, if we keep on removing these unnecessary vectors, we come to a point where the spanning set of those vectors becomes that set becomes linearly independent. So the moment the set becomes linearly independent and it is a span, it becomes a basis set. So it's a basis set for the subspace H. It leads to a very, very powerful theorem, guys, which is called the Spanning Set Theorem, which says that if S is a set of vectors in a vector space V, we are having V1 to Vp, and I take the spanning set of this S, and by default we know that this H is a subspace of the vector space V. Now, if each of these vectors are linearly independent, we are good to go. H is a basis set. But if I find one of the vectors, say Vk, is a linear combination of the vectors of the others, if you remove that, it will still make the new set span the whole set H. We continue this process till we are able to get a linearly independent set. And it's very important, we cannot go till the zero vector. H cannot be a zero subspace. So some subset of S is a basis in H. Okay, so the spanning set theorem simply says that if you have a spanning set, you can basically keep on removing the extra vectors, which are written as a linear combination of the other vectors, and you continue this process till you find the set becoming linearly independent. The moment the set becomes linearly independent, that spanning set of those set of vectors is a basis set. Okay, now I would like you guys to work on these problems from the book, Lay 5th edition, to find which set are the basis set, 1 to 8, 15, 16, 19, 24, and 25. Thank you.